We have the graph of h of x as shown on our diagram here. We are asked to use this graph to find an estimate for the gradient of the curve at the point minus 1, 6. So we're going to find the point minus 1, 6 and then draw a tangent. Minus 1, 6 is here, and then draw a tangent that a straight line that effectively touches that point and looks like it would have the same gradient at that point. So when you draw the tangent, you just got to make sure that you don't overlap the curve either way. So in terms of what I'm thinking, something like that would be okay. Now, of course, there's a little bit of wiggle room for error. So when it comes to drawing your final tangent, what I like to do is find two nice points that you're going to use in order to calculate your gradient. So what I mean by nice points is points that you can accurately read the coordinates of. So this point I've got here at the top, that's actually not too bad. We've got this minus 1.6, 10. If I pick this point here, so that'll be, I'll just write this out now, so you could have minus 1.6, 10 if we end up using that point here. And as far as what I've got here is concerned, I see a 0.6 at that part there. I'm just thinking actually, that's not a minus 1.6, that's a minus 1.8. So I just realized the scale of this is slightly different, so in fact, no, it's not that either, it's a minus 1.7. So just to show why that is, just coming down here, minus 1.7 because of the fact that this is minus 1.5. So minus 1.7, 10, and for this point here, 0.6 is the y, and that, because it's on the y-axis, your x is 0. So 0, 0.6 and minus 1.7, 10 are the points that I'm going to use to estimate the gradient. Of course, there's a bit of wiggle room in terms of really any of the points in that region here, or potentially any of the points in that region there. So whilst what I get is not the perfect answer, it never was going to be, there's a range of values that are acceptable. So from using our gradient formula, rise over run, or the difference in y's over the difference in x's, we're going to get our gradient. So picking 0, 0.6 as our second point is going to give us 0.6 for the y and 0 for the x for the second point. And we have minus 1.7 and 10. So minus 1.7 for the x and 10 for the y. And we're going to be subtracting these away from each other, being careful of the double negative on the bottom. So from that, let me type this in, I'm going to end up with I get negative 94 over 17, which is minus 5.53 if I did it to two decimal places. Now, you're given a certain wiggle room in terms of what gradients are accepted. That there makes sense given my picture here and the coordinates that I have used. As long as your tangent here has two key points that you've correctly identified the coordinates of, and then use the gradient formula to find it. As long as you're within a particular range of values, you will get full marks for it. So the range of values that are accepted based on this mark scheme is anything between minus 6 and minus 4. So as long as you're between these values here, you will definitely get full marks for it. Part B. By drawing a suitable straight line on the grid, find an estimate for the solution of the equation hx equals 7 minus 2x. So hx is the curve that you see here. 7 minus 2x is the line y equals 7 minus 2x. So what we're going to do is draw that line on our graph and then use it to estimate the solution for where they meet each other. So 7 minus 2x, in terms of drawing this straight line, we have, I'll write it in y equals mx plus c form, so minus 2x plus 7. So we have 7 here as being the y-intercept, or minus 2 there with x tells us our gradient's minus 2, so it's a minus 2 over 1. So that means for every 2 I go down, I go 1 across to get to the next point. Being very careful with the scale that's used here. We're not counting boxes. We've got to make sure that we count what 2 down represents in terms of our scale and what 1 along represents in terms of our scale. So that would give us the following, and if I kept going, I'd end up with the following points. Another thing you could do is set y equals 0 and solve for x. If you do that, you'll end up with x is 3.5 as shown here. And of course, I can go back the way here, and the line drawn would be this. So I have to use this to estimate the solution to where they intersect. It is wanting the solution of the equation, which means it's only interested in the x. So what I do here is I'm going to go down to our x-axis here, and anything within this range is going to be accepted based on what you've drawn. So if I actually zoom in here, this is a little squint. It should actually be a little bit to the left. So when I go down here, I'm actually going to pick this as the value. I think that's probably the best estimate that I have. So 2.2 is what I'm going to have as my solution to this, my estimate. So x equals 2.2. And of course it says here to 1 decimal place, which I've done anyway. So if I thought that was 2.21, it's going to be 2.2. If I thought that was 2.18, it's going to be 2.2. Lastly, the equation hx equals k has 3 different solutions for a certain range of values of k between a and b. Use the graph to find an estimate for the value of a and the value of b. So, k is a number. H of x equals a number means that we're intersecting h of x with a vertical line. And that vertical line is going to have the equation y equals k. So there is a vertical line that is going to intersect with our graph and is going to give us 3 different solutions. Now given, and I'll scroll up in a minute, given our graph looked like this, a cubic, we are looking for a horizontal line that is going to intersect our graph on 3 occasions like any of the following. If we have a line that just touches the top like that, that would be no good, because then if it touches here, it only meets it twice. And of course anything above that will give us 1 solution. Anything that just touches here will only meet twice, and of course anything below is only once. So the inequality here is basically saying that the maximum height of this and the minimum height of that are going to be our values. Well, B will be the highest one, the greatest value, and A will be the smallest one, the least value. So we use our graph as an estimate here for what is the height of that, first of all. Now it looks just above 8.2. Like we're so close to being 8.2. If you put 8.21 or 8.22, that's going to be accepted unless there's something about it being whole numbers or decimals. It doesn't really say. Again, you've got the estimate here. So, 8.2 all day long will be accepted. Because I see that just go over a whisker, I'm going to say it's 8.21. But really, it's if you wrote 8.2, that's going to be totally fine. So the highest number there, if I put 8.21, the mark scheme actually says 8.2, but just because of the fact that I can see that peep above, I'm going to make it slightly bigger than it. Then we look for the lowest possible value. Here, this is going to be just before that line, like a smidgen before -4. -4 is what the mark scheme is saying, so -4 would be a perfectly acceptable answer for A. I see it as being just before it, so even if I put -3.99, we're talking just before -4. As long as you've got a ballpark figure that looks right from the picture, you're going to be right. Just because of the fact that mark scheme says it, let me just leave it as -4 and 8.2. Don't really need to complicate it any further. So our interval of equations of horizontal lines that will give us 3 intersections like what we've got here in blue is going to be when A is between -4 and when it's between 8.2. Done.